And we're up. So is there, I gave you that little introduction last time after we went through the test solutions. Are there anybody want to ask anything about last time? I'll give you a couple of minutes a minute or so to remember. You can send me a text message 262-510-2046, or you can use the chat window. Go up to the top left of your Hangouts window. You can click on the little blue icon. Welcome, Brandon. And then you can ask a question that way too. Anybody? Question from last time. We'll dig a little deeper into finding derivatives today then. So I'm going to do my sharing. Screen one. So hopefully you should be seeing 2.1, the derivative and the slope of a graph, which we really started last time. All right. So a little bit of review. Last time we did a derivative, and we didn't do the easiest one. But first of all, just a reminder. If you take a difference quotient and then take its limit as either h, or in this case delta x, approaches 0, then you've got this really powerful calculus thing called a derivative. And that's what we've been leading up to all throughout our beginning, for the weeks that we've had class so far. So we've been kind of getting ready for this all along. So I'm going to dig right into another problem. I don't think this is the exact one we did last time, and I want to show you, there's some variations of directions. I'm diving right away into number 42. This is on page 91 in your book. And there are different ways to end this up. This particular one, you can see I've copied the directions right out of the book. In numbers 37 to 44, find an equation of the tangent line. The tangent line, as you remember from geometry, a tangent line is a line that just barely touches a curve at one point. And, a derivative finds the slope of that line. That's what this whole thing comes from slope. That's really all a difference quotient is. If you remember, it's just a slope, y2 minus y1 over x2 minus x1. And then we threw a limit in there so that h can be shrunk down to nothing, and then we have this instantaneous slope. So on this one, besides the slope, we also want to find the equation. So find an equation of the tangent line to the graph of function f at the given point. For number 42, they give us the function, the square root of x plus 2, and the point they give us that we want to find the tangent line at going through that point is the point 7, 3. If you just if you just check real quickly, if you plug 7 into this equation for x, you'd have the square root of 9, which is 3. So do you see why when you plug in 7 for x, it makes sense that the y-coordinate should come out to 3. All right. So just like last time, this is what we're aiming at, right? A derivative is to take the difference quotient, f of x plus h minus f of x all over h, and then take the limit of that as h approaches 0. That's what we're aiming to do. In order to do that, we have to first figure out f of x plus h. So that's what this line is here for, so that we can go in there and do that. And of course, this time it's really easy. just plug in an x plus h where there previously was an x, and you're going to get the square root of x plus h plus 2. Okay, so now let's start plugging into the limit equation. You could just, let's see. I guess I'll tell you what I'll do. Well, whatever. I was going to say, for the moment, we're only talking about this for the moment. So just kind of center your eyes there first. So all I did here is take the f of x plus h from up here, and I just plugged it in, and then subtract the original function, put it all over h, and take the limit as h approaches 0. Can we substitute? You can see we can't, because if h was 0, this denominator would be 0, and we're out of luck. We can't do anything. Can we factor here to find the limit? No. And we're not going to be able to factor roots on the top. Here's a perfect time for that conjugate again. Just like the one we did last time, I have to take the conjugate of the top, multiply both sides. Maybe this is almost the same problem, except we're going to take it a little bit further. So take the conjugate of this thing over here on the left, and here it is, over here on the right. And now, of course, we have to multiply it by both the top and the bottom. Okay, the nice thing that happened on top is we get the difference of two squares. Goodbye roots. This first guy squared is that thing without the root sign. And then we get this guy without the root sign. Watch out for these parentheses right here. You need to think of them. And then, just like yesterday, what? X minus x is going to be gone. 2 minus 2 gone, and all we have left on the top is an h. And on the bottom we have a mess, but at least what? That h over here cancels. And can we take the limit now? We can, because even though h right here is 0, that's okay. If that's 0, it's gone. It'll just be the square root of x plus 2 plus another square root of x plus 2, which is 2 times the square root of x plus 2. Now, some notation I didn't show you last time is right here. When we put a little apostrophe after the f, that means the first derivative of x. Later, we're going to take the second derivative, and then we might use this notation. I mean, we don't want that right now, but we're going to be using those little. That's right, and yeah, I have to erase. So those little apostrophes indicate the derivative, and this is the first derivative. Okay. Now, if you remember, way up on the top, we were supposed to find the equation. Now we know this is the equation for finding the slope. But we were supposed to find the slope where? When x is, whoops, let's undo that. When x is 7. Okay, so now down here at the bottom, all I got to do is find f prime at 7. So here was the equation for any value of x, 1 over 2 times the square root of x plus 2. But now I want to find it for a specific x, 7. So what's f prime at 7? Just plug in a 7 for x. 7 plus 2 is 9. The principal square root of 9 is 3. And 2 times 3 is 6. There's the slope of our tangent line right exactly at that point, 1/6. Now, on some problems, like if you look in your book, numbers 27 to 36, we would be done, because all they would be asking us for is the slope. All done. On this problem, let me just scoot back up to the top. On this problem, they asked us to find the equation of the tangent line. So in addition, so now we know the slope, but we have to go further and finish it. So now that we know we have the slope, then we come over here and look, and you know how this game goes. You start with your generic mx plus b equation. You plug in your slope, and now we've got this. Now it's time to plug in the one point we know, 7, 3. So 3 goes in for y, 7 goes in for x, giving us this. And then, of course, you have to subtract 7/6 from both sides. And we change 8, another name for 18. I'm sorry, another name for 3 is 18 divided by 6. So we have a common denominator. So 18/6 minus 7/6 is 11/6. Now we got our b, and now we've got it. There's the equation of the tangent line at that specific point. So one more time, from 27 to 36, we would have stopped right up here. All they did there is ask you for the slope. In 37 to 44, or is it further? 37, yeah, through 44, they say find the whole equation of the tangent line, and then the answer is like we found it here on the bottom. But of course, the heart of this whole thing is, do you know how to find a derivative? And that thing in the box. So, all right. Just checking here. Welcome, Sarah. Never did say hi. Glad to have you in here. Anybody else joining us? If you want to ask questions, remember you can go up in the chat and ask. I will try to keep my eyes on that while I'm teaching. And then you can always text me, 262-510-2046. Anybody have a question on 42? I know that may be pretty fast, but this might even be the exact problem we did last time. But we never carried it out with the 0.73. Now we have. I want to do another one of this ilk. Not the easy, these roots aren't the easiest derivatives. So we're going to take one this time. That's a little bit better. Number 44. So I'm going to move to number 44 now. The same directions, different function, and a different point. By the way, does that point match up? If you plug in 2 for x in that equation, will you get an answer of 1, like it says right here? And you do, right? Because if you plug in a 2 for x, you get a 2 minus 1 in the bottom, and 2 minus 1 is 1. 1 over 1 is 1. Okay. So if we want to find the equation of the tangent line, we first have to know the slope of the tangent line, and the only thing that will let us do that is finding the derivative. So once again, we need to start off by finding f of x plus h. Pretty easy again, just stick an x plus h in wherever there was an x before. So now we can set up our derivative, and our derivative says, all right, take the limit as h approaches 0, take f of x plus h, that's this thing on the left, and subtract that thing on the right, that was the original function, put that all over h. The only bad news is now we have what? We have a fraction, and a fraction as part of a bigger fraction, a complex fraction. So we do have to horse around with common denominators. In order to get these two fractions on the top to have the same denominator, I got to determine what is the lowest common denominator. Well, I need one of these, and I need one of these. And sure enough, I just need one of each. What am I missing in the denominator of the first fraction? I'm missing an x minus 1. So we multiply top and bottom by x minus 1. What am I missing in the denominator of the second fraction? An x plus h minus 1. So we multiply top and bottom times that. So right now we're kind of ignoring the h on the bottom, but we will get to that. Yeah, you know what? I'm going to just get rid of this this cover-up thing. And now let's scroll down a little bit. Okay, so now in the next step, and this is maybe getting a little sloppy, we now will have this common denominator of x right here, this common denominator of x minus 1 times the quantity x plus h minus 1. And what do we get on the numerator of the left fraction? X minus 1. What do we get in the numerator of the right fraction? X plus h minus 1. And because of this minus sign up here, I've got to put this in parentheses. Otherwise, I wouldn't, properly distribute that. And of course, I can't forget about h down here on the bottom. So I called it h over 1. You'll see why in a few moments. So what happens on top? What's x minus x? Goodbye x. What's negative 1 minus a negative 1? Goodbye negative 1s. What's left? A subtracted h. So you can barely see it, but here was my subtracted h. Let me scroll a little bit further. So I still have my common denominator, and I still have to divide by h over 1. By the way, do you see that I've inverted and multiplied? I was dividing by h over 1. Now I'm multiplying by 1 over h. And that's where the beautiful thing happens. Of course, this h will cancel with that one, allows us to simplify, and we're down to this guy right here. And of course, I still have to take the limit. My limits are getting sloppier over here. Still need to take the limit as h approaches 0. Can I now substitute a 0? I can, because this just turns out to be x minus 1. So I have x minus 1 times x minus 1. Here it is. There's my derivative. Or you can also put it in this form. Shortcut, x minus 1 times x minus 1 is x minus 1 squared. So there's my general derivative. Again, note the notation, f single prime of x, the first derivative of the function f. Okay, now we'll bring back our point over here, 2 comma 1. What's the derivative when x equals 2? What is f prime at 2? Just like you've learned, what do you do with function notation? You substitute the 2 in for x. Well, what's 2 minus 1 on the bottom there? 1. And what's 1 squared? 1. And what's negative 1 over 1? Negative 1. So now we know the slope of our line. Big step. So now, if you were on a problem from 27 to 36, you would be done. You found your slope. Because we're on the next section, we not only want the slope, we want the equation. So now we do the old algebra stuff. We go back to y equals mx plus b. And we already know this is what the equation looks like, because we have our slope, negative 1. Now plug in the point 2 comma 1. So 1 goes in for y, 2 goes in for x, and we're able to do a little arithmetic and get the y-intercept. Plug it in, bingo. We now have the equation of our tangent line exactly at the point they wanted it. Okay, so we've got 2 of them done. So the first one was a root problem. They're a little bit ugly because you got to use conjugates. They just, I say a little bit ugly because they take a bunch of, it's a lot of ink. This one was a little bit ugly because it was what? A fraction, an algebraic fraction, so we had to do all this common denominator stuff. Let's take one that's, I don't know, nicer behaving than both of those. Okay, it's a good old polynomial. No denominators, no roots. Now if you look to number 46, there is one other little twist in the directions. It doesn't say find an equation at a point. It says find the equation of the tangent line of function f and parallel to this line. whoops, to this line over here. Parallel to that. So instead of giving me a point, they said this, it's got to be parallel to this one. All right. So the good news is, well, first I did a little work over here. I got to get back to red so you guys can see me a little bit better. We can take this equation in the circle here and solve it for y, and now I can see that the slope of the line that they want me to be parallel is -2. So keep in the back of your mind, we want our slope to be equal to -2. Okay, now let's go back. Let's do a derivative of this thing. All right, so f of x plus h, I didn't even figure it out. I mean, isn't that just x plus h quantity squared plus 1? Yeah, so there's my f of x plus h. There's my original function. Put it over h and take the limit as h approaches 0. I hope that's starting to get pretty automatic. Now, when you square this x plus h here, what happens? It's not just x squared plus h squared. You've got that double middle term, right? xh plus xh, 2xh. And then don't forget to, another thing I see students do a lot is they forget to apply this minus sign to the entire quantity on the right. So that becomes minus x squared minus 1. Well, good news. Some things drop. X squareds wipe out. Negative 1 and negative 1 wipe each other out. And you're left with this limit. It's only two terms on top, 2xh and h squared. Can I factor an h out of that? Yep. And what beautiful, why is that important? Because you all see that right here, at this stage, I can't figure out the limit. Why? Because h, when you plug in a 0, the denominator would be 0. So if I can get that h to cancel, praise the Lord. And I can. You can see in the next step here that those nicely cancel. Okay. So now can you substitute 0 in for h? Sure. 2x plus 0, which is 2x. We now have our derivative. That's our general derivative. So 2 times x is the slope of the tangent line at any point x. All right, now we got to get the slope to come out to -2. So the next question is, when will 2x be equal to -2? Remember, we got that from up here at the top when they told us we had to be parallel to a line. So when will 2x equal -2? Well, that's really simple algebra. That's easy, when x equals -1. And when x is -1, what will y be? Go back to the original. If x is -1, -1 squared is 1, 1 plus 1 is 2. The y-coordinate will be 2. So you see that when x is -1, so in effect, this is your point. Okay, now do the whole thing with slope-intercept. Slope, -2. We learned that. Hang on. Yeah, because we knew it had to be what? Parallel to this. Parallel to that. That slope is -2, so our slope must be -2. So we've got this generic equation. Now plug in the point that we just found, and you can see that the y-intercept this time turns out to be nothing. So there it is, or in slide form. There's the equation that we've been looking for. So now you've seen, what, 3 or 4 derivatives calculated. The roots, kind of long. You got to use the conjugates. The what do you call it? The fractional functions are a little bit messy because you got to mess around with complex fractions and get common denominators. When you have just a straight function like this, no denominator, no root, it was a lot neater, a lot less ink. And you know, you'll see some of each of those. Okay, so I'm going to throw up this slide. Just remember now where we've been. The box at the top is a reminder of what we were doing for weeks before we got to calculus, and that was, what is a difference quotient? Just nothing more than a slope formula. y2 minus y1 over x2 minus x1 is where that came from. And then all we do, we learned about limits, and we said, all right, hey, what about when that denominator approaches 0? And if you put that together with the difference quotient, you know, sound the trumpets, da-da-da-da-da, that is a derivative. And we just found, what, 4 of them from yesterday and today. Okay, now, on we go. Here's another fairly easy one. Why don't we do this one? Get another practice session in. This one's fairly easy because it's just a good old polynomial. A little more complex than the last one. Why? Because when you find f of x plus h, you got to plug in x plus h twice, right? You got to plug it in both places where there's an x. So here's I'm finding my f of x plus h. So you notice I had to plug in x plus h the first time and the second time. All right, now you got to hack that out. So there we go. X squared plus 2xh plus h squared minus 3x minus 3h plus 6. And then here I use the vertical subtraction. Let's subtract the, you know, this is the minus f of x part. I lined them up so the like terms are underneath each other. You can see the x squareds drop away. The 3x, the negative 3x's go away, and this is go away, and all we're left with is this numerator right here. 2xh plus h squared minus 3h. I still can't substitute because there's that crazy h on the bottom. However, you probably noticed there's an h in all 3 of the terms in our numerator, so I can factor, which I did right over here. I can factor the h out, cancel it. Now can I take my limit? Can I substitute a 0 in for h now? You bet. It's just 2x minus 3. That's supposed to be a minus 3 here. So there's our derivative, 2x minus 3. And now, I mean, and that's it. Here's a case. If I asked you, hey, what's the derivative when x equals 5? You could just say, well, it's 10 minus, it's 7, because you just plug in a 5. What's the derivative at x equals negative 17? Plug in a negative 17 and calculate it out. So this is literally a formula for the slope of the tangent line at any point x. And that's what a derivative is. Okay, how are we doing here? About halfway done. I'm going to see what okay, so this is the one we just did. Let me look at another one here. Yeah, so this is just another view of what we do when we find a derivative, okay? I mean, you remember this map from the very beginning? We had this gap h down here on the bottom, right here. You know, a distance of h from this coordinate over here to this coordinate over here. And all the derivatives is saying is we're going to shrink h to nothing. That's the part where we always wrote this down on the left. Remember we wrote? So what you're doing is taking this gap right here and you're shrinking it. You're pressing on it from left and right. And by the, I've got a little, I think I've got an animation in here. Yeah, here it is. So here's what's happening. We're taking the h right down here and we keep shrinking it until it approaches 0, and now we're down to 1 point. You know, and then it's just the animation over again. So the whole idea is we're shrinking this triangle down until these 2 points actually join together and become 1 point, you know, right there. So that's why we can make this really weird claim that we can go, I mean, we can go anywhere we're finding the slope at any instant. It's all because of that slope and especially the magic of the limit. Okay. So maybe a little backwards, but here are the things they're trying to show you in this lesson. We have been working on this, finding tangent lines to a graph at a point. We've been finding the tangent lines. We've been more than approximating. We've been finding them exactly. We use limit definition to find slopes. And the only thing maybe we need to talk about is that last one a little bit. Describe the relationship between differentiability and continuity. So, I mean, if we had a graph that had 2 parts like this, we've seen graphs like this that maybe have a vertical tangent line at x equals 0 like that. Well, can you find a derivative at x equals 0? How in the world can you pinch h down to nothing when we don't even have a graph at 0? So what they're trying to just remind you that continuity, if the graph is discontinuous, then you can't find a derivative. So this technique I've been showing you assumes that you've got continuity. If you don't have continuity, well, we're both up the creek. You cannot find a derivative when a graph is vacant or gone. Okay. There's just a couple of views here from the book that talk about this. I encourage you to read what's in the book. See here, they're showing right up here on the top. They're showing a line that's tangent to the curve. I should have gone back to red. Like here, you see here too, down at this curve. These are all tangent lines to a curve at a point. All of these. That's what we've been finding in these problems we've been doing. You know, we all remember it in geometry from a circle, but it works with other algebra curves too. And then I just want to do a shout out to Isaac Newton, one of the co-discoverers of calculus. The other one, by the way, is a German by the name of Gottfried Leibniz. Those two guys, basically almost at the same time in different countries, England and Germany, discovered the technique that I just showed you, finding a derivative. And what a huge leap in problem-solving ability. There's another. Okay, so I'm just going through summaries here. Oh yes, here's something I need to point out to you. If all you do is find the slope, like I did that first day, remember that? I took the y, you know, I just did a slope formula. That is called average rate of change. Okay? You need to know this. They're going to ask you in the book sometimes to find average rate of change. All you need to do is find the slope. That's it. But if you just do one thing, put a limit on there, as h approaches 0, you now have the exact rate of change. So you can see the leap. I mean, average rate of change, that's kind of nice. But can you believe we can actually calculate the exact rate of change right on the schnozola exact? That's what this limit added onto the difference quotient does. And So anyway, you're going to see some problems will say, find the average rate of change. And then others will say, find the exact rate of change. Well, the technique I've been showing you today is this one down here, finding the exact rate of change. How do you find the average rate of change? Just take the two ordered pairs and, do the old slope formula. That'll give you, that's all this is. I know the slope is different up here, but really that's all it is if you have the two ordered pairs. To know that, I don't know which problems, but you're going to see that some of the work either today or other nearby lessons will ask you to differentiate between those two rates of change. Okay, here's another easy one. I'm going to skip this. We've done, I think, enough of those. Let's see what I have here. We've already done that one about 100 times, so we don't need to do that again. Let's just look at one this is a polynomial. We'll do this one yet. And we're going to find the derivative. What's the only thing, this is a good old polynomial. No denominators, no roots, so it's pretty straightforward. The only thing one has to concentrate on is we got some higher powers here, and we have 3 x's. So every place there's an x, we are going to have to find f of x plus h, and it just makes it longer. So here's what you have to do to find f of x plus h. Okay? So I got to take 3 times, instead of x cubed, x plus h cubed. This is just literally raw substitution. Plug in x plus h wherever there is an x, and that's 3 places, right? So after I did that, and by the way, you gotta, this x plus h cubed, you gotta hammer that baby out, and that's no small task. You have to do x plus h times x plus h, and when you get the answer, which we've been doing it, is x squared plus 2xh plus h squared. You got to take that trinomial and multiply it by x plus h a third time. There is no shortcut. Finally, when that's all done, you still have to multiply it by the 3 that was out there. That's what I'm doing here. And then this one you have to take, it's a lot of horsing around, but not that difficult. And by the way, here it is. That whole crazy thing is f of x plus h. And there's no like terms. There's nothing else that can be combined. Now you subtract the original f of x. I line them up. And you wind up with this big old long hairy thing. It looks like it's hopeless because you can't substitute 0 in for h. But, of course, beauty, you can. Every term on the top has an h. Therefore, we can factor the h out just like we've been doing, and we can cancel. Now, can we substitute h equals 0? And the answer is we can. And get this thing out of the way here. So, all the h terms basically what? Drop out because h is 0. What's left? 9x squared minus 4x plus 6. Derivative. So, I guess I should have qualified. If it's a polynomial like we had in the beginning here, yes, we don't have to worry about conjugates, we don't have to worry about common denominators, we don't have to worry about complex fractions, but it still can be a really messy substitution because every place there's an x, you have to plug in x plus h and crank that sweetheart out. So I think it's important that we have gone through and seen that. Now, I've been doing more of the harder problems. We should at least talk about the easier ones. So if you look in your book, what about the ones way in the beginning? Like, what about that first part where it says number from 15 through 26 in your book. So let's take a look at number 15. Okay, here's what the book says. In exercises 15 to 26, find the derivative of the function. Well, look at the function. Whoops, let me undo that. Let me use my red. This is the whole function. Now check this out. What's f of x plus h? Plug in an x plus h wherever there's an x. There isn't even an x. So it's the same thing, 3. So look what happens when you substitute this in. You get this. And what do you get on top? A 0. And what's 0 over anything? So, I mean, that's the derivative. We're all done. So, I wanted to warn you, what do you do when there's no x? Smile, because your f of x plus h is incredibly easy in a problem like that. Okay. How about number 20? Also from that first section in the starting with 15. So here I guess let's just do one more here. So here's your function, 1 minus x squared. Find f of x plus h. That would be this guy. X squared. Remember, x plus h squared is x squared plus 2xh plus h squared. And I got to subtract that whole thing. So I get a lot of minuses there. Okay? So here it is, finally written out. Now subtract the original function, 1 minus x squared. What's left? The 1's drop away, the negative x squareds drop away, and you have this. And again, beautiful. You can factor in h out of the top and joyously cancel. Now can you substitute in your limit? Can you plug in a 0 for h? Sure can. You just get negative 2x, and there's your derivative. Okay. Maybe I gave you enough to chomp on. Let me show you what the assignment is going to be. You probably know this already, it's on the website, but every other odd, starting with 1 and ending with 1. So what is that, 15 or I think it's 16 problems to work on? So I dumped a lot on you today. What kinds of things would you like to ask me about? Let's make use of this format now. Please ask. Any questions? You can speak up, turn your mic on, or do it in the chat room, or do it by text message, or, I don't know, email me, call me.
Can you go back to number 20? You went through it a little fast.
You bet. 20. See if I can find it. Okay. I believe this is the one you're looking for. Am I in the right spot for you, or do I need to scroll?
Yeah, you're good.
Okay. Other people, you can certainly be formulating your own questions here. That still might be too sloppy, so if you want to ask me about that, go ahead.
I'm good.
Other questions? Thank you for asking. Aren't you wow. Is it snowing hard there? It sure is here. A lot of flakes coming down. Kind of glad I didn't have to drive in this. Okay, well, it's getting pretty quiet. You certainly can, you know, send me questions after we're done here. The video should be up in just a few minutes. I'll have the link up. And of course, the date is what? 3/1/2016. Thank you, everyone. You can still ask me questions.